Here is another example on the root locus. So here is the given open loop system. K times s plus 1.5 by s times s plus 1 times s plus 5. So basically here you can see that that's a g of s. This is the open loop system. Okay, y as an output, u as an input, and it has a unity feedback. Okay, so y by u, okay, that's a unity feedback system, will have a transfer function of g of s over 1 plus g of s. Now step 1, locate the poles and zeros. So we have poles, the denominator, make the denominator equal to 0, s equal to 0, s equal to -1, s equal to -5. That's poles. And 0, make the numerator equal to 0 to find the zeros. I end up with s equal to -1. Now label them in the graph. So in step 1, I'm labeling all the 3 poles I have at 0, -1 and -5, and there is a 0 at -1.5. This value is -1.5. Now find out where the low key on the real axis. So always start walking from your right to left. As long as you have odd number of poles and zeros, there is a low key. Okay, so from here, okay, this is odd number for sure. There is low key here, okay, until this. So basically coming from there, coming from out there. Now here in this area there is no low key. Yeah, I mean here, because it's on your right hand side. Once you pass the second pole at -1, you end up with having 2 poles on your right hand side, so there is no low key here. Once we pass this, there is a low key here. So we know that the root locus or low key always reach the 0, coming into 0 or going out of the pole. Okay, those are the important points. So this low key will be here until this point. Okay, so this low key is coming in this direction. So the thick red line indicates the low key. So basically whatever the low key here, it's going to break away. So we'll move to point 3, step 3. So step 3 here, find the angle of asymptotes and centroid. So theta equal to plus or minus 180 times 2q plus 1 over n minus m. And here number of poles, which are 3, number of zeros, which are 1. So q equal to 0, 1, 2, 3, etc., up to n minus m minus 1. So we'll end up with only 0 and 1. So theta 1 equal to 180 over 2, 90 degrees. Theta 2 is also plus or minus 270 degrees. So you can see this is plus 90, this is minus 90. Okay, and I can say 270, this is plus 270, and this is minus 270. So basically you will end up with 2 lines, and centroid is minus 2.25, which are sum of poles minus sum of zeros over n minus m. So 0 minus 1 minus 5 minus of minus 1.5 over 2. So end up with minus 2.25. So it will be on the graph. So here is the graph. Minus 2.25 is somewhere here. Okay, so that's a centroid. Now we'll have asymptote. Okay, this is asymptote. That is from step 3. Now step 4, find breakaway or break-in point. So for that we need to find the closed loop transfer function. Closed loop transfer function is y by u equal to g of s over 1 plus g of s. So we end up y by u equal to this equation. Now the characteristic polynomial is nothing but the denominator of that closed loop transfer function. Make it equal to 0 and find the k value. Once you have the k value, find dk over ds. Okay, since you have u by v, you have to use the u by v formula, u prime times v minus v prime times u over v square. Okay, so make it dk over ds equal to 0. So we'll end up with this. Now it's a third order system, or third order characteristic polynomial equation. So find s values. I end up with s equal to minus 0.6, s equal to minus 2.3 plus or minus j 0.89. Now substitute this s values in the k, okay, in the characteristic polynomial equation to find k. So when I substituted s equal to minus 0.6, k value is 1.17. If k is not positive and real, it's not a breakaway point. So here, when I substituted s in the characteristic polynomial equation, I end up with the positive value, so it's sure that's a breakaway point. The remaining 2 points are not breakaway points. I mean, I didn't show it here, but when you substituted imaginary values in the characteristic polynomial equation of the closed loop system, it will end up with not a real number. So here the breakaway point is s equal to minus 0.6. So, and you can see the breakaway point is going to be between these two, because here it is going to divide. So minus 0.6 is right there. Okay, we know that when the low key is leaving the real axis, it will go away at 90 degrees angle. Now step 5, find the angle of departure and arrival. That's only if there are complex poles or zeros. Here I don't have any complex poles or zeros, so don't need to find angle of departure and arrival. Step 6, find the crossing point of imaginary axis. So take the characteristic polynomial equation of the unity feedback system, closed loop system. Now substitute, that's the function, characteristic polynomial equation. Substitute s equal to j omega. Now put imaginary part equal to 0. So in this equation, make imaginary part equal to 0. When I put the imaginary part equal to 0, I end up with omega square equal to 5 plus k. And real part equal to 0, end up with k value as minus 6.67. So to have the crossing point, k value must be a positive and real number. So here it's not a positive number. That indicates that it is not crossing the real axis. So basically what is going on here, this will be going towards to asymptote, okay, towards the asymptote. So same thing here, it's going to go towards the asymptote. These asymptote and low key, they're going to meet at infinity. Okay, so here, I mean, we know that here more number of poles than zeros, so it always starts at a pole, ends at 0. If you don't have enough zeros, it will end at infinity. So these two low keys, they are ending at infinity, same as the other examples. Thank you. With this, I'm done with this root locus chapter. Thank you.